A large, round table hangs on the wall of the castle in Winchester, United Kingdom. Many would like to believe that this is the Round Table of King Arthur, who, so legend would have it, was at the height of his power in about AD 500. If the table dates from this time, what proportion of the original carbon-14 would remain? In 1976, the table was dated using the radiocarbon technique, and 91.6% of the original quantity of carbon-14 was found. From when does the table date? There are two questions to solve here. The first is that if the table is in fact from AD 500, what proportion of the original carbon-14 would remain today in 2025? The second is that if in 1976 the table was dated and 91.6% of the original quantity of carbon-14 was found, what year then does the table date? Does it in fact date from AD 500? Before we can solve either of these questions though, we actually have to first derive an equation describing the amount of carbon-14 over time. To derive our equation, we are going to solve the following differential equation. The rate of change of the amount of carbon-14 over time is equal to the amount of carbon multiplied by some negative scalar constant k. To achieve a particular solution, we are going to suppose that there are n naught radioactive atoms at time equals 0, meaning that n0 is equal to n naught, providing us an initial condition. There are two cases we have to consider when solving our differential equation. The first is when n naught is equal to 0. The second is when n naught is not equal to 0. When n naught, which as a reminder is the initial amount of carbon atoms, is equal to 0, the number of radioactive atoms in the material can't decay any further over time. So the solution to our differential equation when n naught is 0 is 0. For case 2, we have to integrate our differential equation. To start, we are going to divide both sides of our differential equation by negative kn, separating our differential equation. Next, we're going to integrate both sides of our differential equation with respect to dt. After integrating, we obtain the equation negative 1 over k multiplied by the natural logarithm of the absolute value of negative kn is equal to t plus c1, where c1 is some arbitrary constant. Now, we must go about isolating for n in this equation to give us the solution to our differential equation. The first step in doing so is multiplying both sides by negative k, removing the negative 1 over k fraction from the left-hand side. We are also going to say that c2 is equal to negative k c1, replacing our previous constant. Using the definition of logarithms, we are going to rewrite our logarithmic equation in exponential form, giving us e to the power of negative kt plus c2 is equal to the absolute value of negative kn. We're going to take the inverse of the absolute value of both sides, and then we're going to set constant c3 equal to plus minus e to the power of c2. Finally, we are going to divide both sides of our equation by negative k, isolating n entirely. We are going to set new constant c4 equal to negative c3k. This provides us our general solution. Nt is equal to c4 times e to the power of negative kt. Now, to obtain our particular solution, we are going to use our initial condition, n0 is equal to n naught, to solve for c4. Doing so gives us that c4 is equal to n naught, and our particular solution is thus nt is equal to n naught times e to the power of negative kt. We find then that the number of radioactive atoms in some sample of material at time t is therefore nt is equal to n naught e to the power of negative kt.
Now we can begin to answer the following question. If the table dates from 500 AD, what proportion of the original carbon-14 remains today? The proportion of carbon is determined by taking the amount of carbon today and dividing it by the amount of carbon originally. We can use our derived formula to calculate this. If we take N naught to be the initial amount of carbon-14 and N of T to be the amount of carbon at time T, where T is today, we can divide both sides by N naught, giving us the desired ratio. This is possible because N naught is not equal to 0. However, we still need to determine the unknown constants K and T. So K is the half-life of carbon-14, which is a constant given in the textbook as ln of 2 divided by 5,700. And T is simply the amount of years that have passed since 500 AD, which is 1,525. So putting those numbers back into the equation, we get approximately 0.8307. Therefore, we can conclude that if the table was found at 500 AD, approximately 83.07% of the carbon-14 would remain today. Now, the second part of the question states that in 1976, the table was dated using a radiocarbon technique, and 91.6 of the original quantity of carbon-14 was found. We now have to answer, from when does this table date? So since the proportion is 91.6, we can take the equation we had from before and replace NT divided by N naught with 0.916 and setting it equal to E raised to the half-life of carbon-14, multiplying it by -1, and T, we can now just solve for T. So taking the natural log of both sides, we get ln of 0.916 is equal to -ln 2 divided by 5,700 times T. So then dividing both sides by -ln 2 over 5,700, we get T is equal to ln 0.916 divided by -ln 2 divided by 5,700. And we get the value T is equal to approximately 721.5, which we round down to 721. So since the dating was done in 1976, the table must date to 1255 AD because 721 years have passed, basically, since the creation of the table. So it looks like King Arthur did not use this table in 500 AD.
Hey everyone, my name is Josiah Yap and I will be presenting question 5.2 stated here. Find the function f of x defined for negative pi over 2 all the way to pi over 2, which is non-inclusive, whose graph passes through the point 0,2 and has a slope negative tan x. Alright, so just a slight visualization. So basically what we want to do is we want to find a function that passes through this point, has this slope, mind you. It has this slope, but not around this domain. But it's the slope. This is the slope that we're given, not the actual function itself, of course, because that's what we're trying to find. To find within this range, it's non-inclusive, because we do this because if we plug in negative pi over 2 or pi over 2, we get undefined values in these points. So, since we're given the slope, we know that the slope is basically equal to the derivative at that point, right? Like the slope of the tangential line should be equal to the derivative of that point at that point. So we can express the slope as a separable differential equation. So we can say that the function, the derivative of the function in terms of x is equal to negative tan x. Now we can just integrate and solve both sides. The left hand side is simply the antiderivative of the derivative of the function of in terms of x, so it just should give us the function of x back again. The right hand side is negative tan x dx. Now we don't have a direct formula for this, so we're going to have to use our techniques and tools for integration. So to make it easier, let's first start by splitting it up using a trig identity. We know that tan x is equal to sine x over cos x. We can now use our u sub to solve. For this problem, we will choose u equals cosine of x. This derives into du equals negative sine x dx. Plugging all these values in, we can see that this this turns into 1 over u du. This is something we have a formula for, so this makes it a lot easier to deal with. Let's do our actual integration. We know that the left hand side, like we stated before, is simply the function of x, and the right hand side is ln of u plus c. Now we defined u as cosine of x, so we plug it back in. So we are left with function of x equals ln of cos x plus c, which is the general solution, and we need a particular solution such that the function passes through 0, 2. Now, how do we do that? Well, we simply have to plug in these coordinates respectively. 0 should go into the x, and 2 should go into the y, or the f of x. So, using that value, we plug it in. Now we have 2 equals ln of cos 0. Cos 0 is simply 1. So we have ln of 1, and ln of 1 is simply 0. So we're left with c equals 2. Now we replug that back in to the function, and we have function of x equals ln of cos x plus 2 for this domain. Negative pi over 2 less than x, which is less than pi over 2. So around there. Now we can double check our solution. So if we plug our function of 0, let's see if it will equal to 2. So we plug it in. Ln of cos 0, ln of 1 plus 2. Ln of 1 again is 0, so 0 plus 2 equals 2. So the point checks out. Now let's check the derivative. F prime of x equals negative sine x over cosine of x. And we plug in 0. And that's simply equal to negative tan of x. So the slope checks out. So we've arrived at the solution, and we've checked it, and it holds. Thank you for listening.